we sum the bit we want to solve, if it is not even, doesn't mean to have some mistake in the bit.
What would a condition look like in this?
Sorry?
What would a condition look like? A constraint, what would that look like for me?
It's what I asked. It's what I asked you. You need to write this probability actually as an exercise.
No. The code. So for example, the constraint.
The code is the same.
The code is the same.
Yes. You can use the same code to communicate through these two different noisy channels. Do you think that you will make more errors? You have a higher probability to decode with errors for a BSC or a BSC channel?
For the bit, if you get question mark, you can see question mark.
Yeah.
Yeah.
What do you mean you can see question mark? Yeah, you know that you, no, it's, the question mark means you receive nothing. The bit is erased.
Yeah.
But how do you tell which bit is it?
It's because there is a notion of time. If you want to receive one bit every second, and sometimes you receive nothing. So it's question mark. The bit has been erased.
Okay.
And then the next bit, maybe you receive it.
Oh my god, it's like if someone was sending data back to space.
Yeah, if you want.
And
some are erased, yes.
Oh.
You didn't understand that?
No, I did understand that,
okay.
But it made a lot more sense just now.
Okay.
Okay. I think in this, we see something.
Speak louder each time, please.
I think someone will say something in the Zoom.
If these, you want to say something?
Yes.
You're unmuted.
Wants to speak?
So in the new case, the BSC have more errors.
Yeah.
Yes. Why?
So if we compare it to the first one, the erase channel, in the first one, we already know if we don't receive a code. We already know if a bit isn't received. But in the second one, we don't even know if we get the symmetry or we get the right one.
Exactly, but you don't know when a bit is received, not a code. The code is
yes.
That's exactly that. The thing is that with the eraser channel, when you receive a bit, you know there is no mistakes.
Yeah.
You know exactly that this is the bit that has been transmitted.
Yeah.
Sometimes you don't receive something and the bit is totally lost. Okay. But in the second case, it's worse because you always receive things and you never know which one have been corrupted or not. Okay, because each bit you receive may be a bit that has been flipped or not. You don't know. Okay?
So what is the BSC used for? Cryptography?
No, these are models for communication of bits, and this typically model Wi-Fi communication, for example. Short distance communication of bits is usually modeled through this type of channels. Yeah. So yeah, the BSC is more difficult to decode. It's more difficult to correct the errors in the BSC. Okay? Good. All right, so I'm again way too slow, like way too slow. So yesterday we talked about a lot about the entropy, and we interpreted that as the information content, the expected information content of a random variable, or the expected unpredictability, uncertainty about it. Okay. Let me come back to a few things that we've shown about it. So the entropy, let me recall the definition. It was sum of x of px log 1 over px. We know that this is always non-negative for discrete random variables. Did you try to prove that h of x, y is equal to h of x plus h of y if x is independent of y?
Did not get it.
Okay, so do it. It's like one line of computation. Okay, so the information is additive for independent random variables, as it should. Then I also define the conditional entropy. which is sum over xy belongs to x, y of p of y times p of x given y log of 1 over p of x given y. And this, you can also write this as p of x times y. Okay, by the definition of conditional distribution, it is the same. How do we interpret this conditional entropy? So again, you choose if you prefer to interpret that as a measure of information or as a measure of uncertainty. Let's say as a measure of information. This is the information you gain when observing the outcome of x, the expected information you gain when observing x, given that you already knew y. Given that y was not random anymore, you already observed its outcome. Okay? Or as a measure of uncertainty, h of x given y is the remaining uncertainty about the random variable x, given that you already know y. Okay? So, for example, if you take the coin tossing experiment, I toss 10 times a coin, and I define one random variable, which is the number of heads, and one random variable, which is whether I got more than half heads or not. Okay? You see that if and let me call this second random variable y, while the number of heads is x. You see that you have less uncertainty about the number of heads if I tell you that there are more than half, so more than 5. Okay? All right. And so h of x given y must always be less than h of x. If I tell you anything, even this thing that I tell you does not bring information about x, I cannot increase the uncertainty about x if I tell you something. Okay, any information reduces the uncertainty. Okay, and you have equality when the random variables are independent. Okay, if y and x are independent, of course, the uncertainty about x remains the same if I tell you the outcome of y. If they have nothing in common, if they are totally unrelated. Okay? You should try to prove all these things. They are very basic things to prove. Huh? It's just one line of algebra for all of this relation. Another nice property that h of xy, this is called the chain rule, is equal to h of x given y plus h of y is equal to h of y given x plus h of x. This is the
Base formula.
You can derive that from base formula or from just the definition of conditional probability actually.
Yeah.
You don't need base formula.
Yeah.
This says that the uncertainty about x and y is equal to the uncertainty about y plus the remaining uncertainty about x if I was telling you what y is. Or said differently, the information carried by x and y is equal to the information carried by y plus the remaining information carried by x if you already know y. So it's very natural, this relation, if you think like this in terms of information or uncertainty. And of course, the reasoning is symmetric, so you can change the rule of x. This is called the chain rule. Another nice property that strongly suggests that all that is a proper measure of information. If you take any function of x, then the entropy of f of x given x is 0. Because f is a function of x, it means that if I tell you x, there is no uncertainty about what is f of x. You just need to apply the function. So f of x is not any more random. There is no more uncertainty about it when I tell you x. And therefore, this has to be 0. Okay? Or said differently, if I tell you x, you don't get more information by applying a function of it, because this is just an operation you do. You could take another function, you would get a result. Okay. Okay, I will stop there. You should try, so there is this exercise too that I wrote in my notes. Try to prove these things. I think it's important that you, okay. Now you are at the level of, there are the concepts, but you should be able to do computations. Okay, so you should be able to prove this. And these are just basic things that follows from properties of the log and the definitions that we introduce. And if you don't manage to prove them, just come to see. There is also the exercise 3 that I advise you to have a look, which is very nice, but I won't do now. Okay, so let's try to make a first connection between what we discussed now, which was really information theory, okay, and statistical mechanics. Okay. So look at the exercise 4 in my notes, if you have them. Let's do it.
You have the arrow, right?
Yes. You already tried?
I read.
Okay.
I will try to solve the other problem.
Okay. So the exercise for next time is prove all the as many properties of the Shannon entropy as you can. Okay. And by proving, it means really a series of equalities that is the result. Okay. Okay, so let's consider a very simple model where we have a square grid made of n sites. Okay, and there are n possible particles that live on this grid. And we will assume really the simplest possible settings. The particles are independent of each other. Okay? So they can be, each particle can be located at any site on this grid. You can have more than one particle on each site. Okay? And essentially, they just move around like this randomly, and at any time they can be anywhere on this grid. Okay. All right. So I would like to know, what is the Hamiltonian of this system? They are all independent like this. So essentially, it costs nothing for the particles to live on the same side. They can be randomly at any position. So what should be the energy? Sorry?
Is it constant?
Yes, it is constant. And if it's constant, we just can say it's zero. Whatever constant is the same. Okay. As long as the energy is constant, it means that all microstates are equiprobable. So yes, the energy is constant. Okay? Because there are no interactions between the particles, and the particles move freely. So the energy is constant. It's not a function. So if I call sigma the vector that describe the position of each particles. Okay, so each position can be from 1 to n. There are n sites, big n sites, and we have little n particles. So this vector, this microstate is what? Is a vector where each component can be between 0 and 1 and capital N, which is describe the site at which the associated particle lives. Okay? So you understand this, why I wrote this? Yes or no?
Yeah.
Okay. So here the Hamiltonian is actually just a constant. It does not depend on these configurations. So if you want, we are in microcanonical ensemble, or equivalently, we are in the canonical ensemble at infinite temperature. Okay, because we said that at infinite temperature, the particles do not interact anymore in the canonical ensemble. Okay?
Yes.
So now I would like you to compute the entropy of this system. And by entropy, really, I mean the Shannon entropy associated to the Boltzmann distribution of this system. So do you really need to compute anything? What did we say in the microcanonical ensemble, where if you have a random variable, here the random variable is this sigma, it's the configuration described by this probability. By which probability? By the canonical, by the uniform distribution, okay? So what is the entropy of the uniform distribution directly? We computed it yesterday. You knew it already from the first week. When you say something, say it. Don't. There is no KB here.
It's log
of. You say things, you say half, so that you know you
No. It's
be confident in your answers. If it's not correct, it's fine.
log
But
of the carbon.
yes, the entropy associated to this random variable is just the log of the configuration space, which is what you wrote, log of omega. Okay, it's the microcanonical entropy. Okay? And what is the cardinal here in this case? How many configurations there are? You have n possible sites, little n particles.
N raised to n.
Which one?
N raised to n. Big n.
So big N.
Raised to small n.
And combination.
What does it mean, combination?
No, nothing.
Big
Again, we're using this word. Nothing.
So you say big N?
raised to small n.
Yes.
Yeah.
Okay. The first particle has capital N possible configuration, states. The second particle has also N. They're independent, so you just multiply. Okay? Which is N log N. Okay? Good. So you see that the entropy scales linearly with the number of particles, as it should. It is an extensive quantity. Okay. Now imagine that for some reason we put a wall here in the middle of this box, and so there are half of the sites that become available to the particle. What is the entropy now? Yes, the entropy becomes ln of n over 2 to the n, okay, which is n log n over 2. So the entropy has been reduced, okay? Okay. So thermodynamics, what is the second principle of thermodynamics?
Entropy. Entropy is greater.
It's greater than what? Go for it.
Entropy is greater or equal to 0.
The entropy.
Sorry.
No, this is not. Speak louder, the others must hear you.
Entropy, the change in entropy is always positive.
Yes. If you take a system and you let it evolve, an isolated system without external force, if you let it evolve towards the equilibrium, if you let it relax, the entropy can only increase. Okay? And once the entropy reaches its maximum value, the system is at equilibrium. Okay? So let's try to understand this with our simple model here. So let's say that at the beginning we trap these particles in this half box, okay? And we are at equilibrium, so the entropy is this, okay? And now we remove this wall, okay? What will happen? The particles will diffuse, and they will occupy all the space homogeneously, and you will reach a new state where now the entropy will be this. Okay, so the entropy increase, indeed. Okay, but actually, the fact that the entropy can only increase is really at the macroscopic level, the statistical effect at our scale. But in reality, if you think about it, and this question should ring a bell because this is the kind of questions I asked to you during the interviews. If the particles are independent, that can be at any site in this box at any time, there is nothing that prevents all the particles to suddenly gather on the same side of the box, to all be on the left side, for example. Okay? So what is the probability of this event? Probability that all particles in the left.
Low.
It's what?
It's low.
Yes, but how low?
Zero.
No.
No, not zero. Without any external forces.
There is no external force. There are just these particles in the box that can be at any position at any time.
1/2 elevated to the number of particles.
Yes, exactly. Okay. Because the first particle has one chance of, they're independent. So you just multiply over I the probability that particle I is in the left. Okay. And this is 1/2 for each particle. So you get 1/2 times 1/2 times 1/2 for each of them. So you have 1/2 to the power n. That's correct. Okay. And you see that this number is ridiculously small when n is large. It's exponentially small in n. Okay. So you see that the reason we do not observe that at our scale, that it looks like the entropy can only increase, is because the event where it would decrease is so, the probability of an event leading to a macroscopic decrease of the entropy is so small that it just never happens. Okay? But there is nothing in the fundamental laws of physics that prevent the entropy to reduce. It's really a statistical effect. It's just that such events are exponentially improbable with the system size, with the number of particles, and therefore we just never observe them. Because the type of systems we describe by the statistical mechanics are made of billions of particles. So exponential minus 1 billion is 0 essentially. Okay, even if you weight the age of the universe in front of the box, it will never happen yet. Okay, because the probability is just so small. Okay, but there is nothing in the physics, in the rules of quantum mechanics that prevent that to happen. Okay, so the fact that the entropy increases is really a statistical effect. It's because a macroscopic state, here described by the fact, if you look at the density of particles, it will be homogeneous. This is an order parameter that describes the model. Okay? You see that the macroscopic state corresponding to having particles homogeneously placed in the box has an entropy higher, has a macroscopic entropy which is higher than the state corresponding to particles on the same side. And this is coming from the fact that it has much higher probability for the particles to be homogeneous in the box. Okay? Another example, which is actually the very same example, just with other words. If you think about playing billiards, it's called billiards. Okay, you play billiard. You start from an ordered configuration where all the balls are in the triangle. Then you start to add temperature. What does it mean? You play. Okay. And what happens is that the balls will statistically spread homogeneously on the billiard. And you can play as long as you want. They will never gather back as an ordered configuration. Okay? But actually, there is nothing in the laws of mechanics that prevent that to happen. If you were actually able to compute the absolute perfect trajectory that the initial condition you need with which you need to hit the ball, you could gather all of them. Actually, there is nothing that prevents you to do that. It's just that there are so many other possibilities that lead to a disordered configuration that this never happens. Okay? So the entropy corresponding to a billiard disorder, okay, is higher than when it is ordered. Okay, and this is what we observe at our scale. This is what we interpret as the arrow of time. The fact that we see things going in one direction of time, it's because systems are evolving towards states with higher entropy. Okay? If you would play the billiard like this and suddenly you make the perfect shot and the balls gather again, or you think that you're getting crazy, or you think that time flipped. You would interpret that as a time flipping, okay? But it would not be time flipping. It just would be the occurrence of an extremely improbable event, okay? If you look at a ball in which there is gas, if you suddenly see all the gas gathering on one side, you would have the impression that the time is reversed. But it's not that time is reversed, it's that something extremely improbable happened. And something very improbable happening translates into reduction of entropy. Okay? You get a sense of what I say, or?
I have a question. I'm a little bit confused about n power n.
Yes.
Since if you consider, for instance, we have this side, 1, 2, 3, 4, 5, and then we have just say 3 particles. In this case, we can put 3 particles in
at the same spot.
At the same spot.
Yeah.
Oh, okay. And when at one time we can put all the particles at the same cell.
What do you mean at what time?
Since I think we have one configuration where we can put 2 particles in the same cell. And in which case we can say, okay, we can add 2 particles in the same cell.
Your question is not very clear, I'm sorry.
Okay, here we can put 2 particles or n particles in the same cell. And sometimes we talk about the distinguished and indistinguished particles.
Okay, distinguishable particles, yeah.
Yeah. And when we can add all the particles in the same cell, you can use this formula.
Yes, yes. Here it's because the particles are allowed to sit at the same site together that this is the number. If I would consider the case where particles cannot be more than, you cannot have more than 1 particle per site,
yeah,
it complicates the counting of the configurations because you start to have interactions actually. If 2 particles cannot be on the same site, it means that in the energy, you have something that goes to infinity when there are 2 particles at the same site, which prevent them to be at the same site.
Since in some cases,
it becomes a combinatorial problem to count these configurations. It's more complicated.
Okay. In another case, we use combination.
So
to find the number of possibilities.
Let's say let's say that now you can have a single particle per site.
Yes.
What would be the cardinal of the configuration space in this case?
And since we have n particles, small n particle and n site, that means the number of possibilities should be the combination of small n in n.
So yes, so the first particle, okay,
yeah,
it has n possibilities.
Yes.
The second one, it has n minus 1.
Exactly.
Then n minus 2.
Till n minus n.
Till n minus n plus 1.
Yeah.
Okay?
Yes, sir.
And this is what? This is n factorial over n minus n factorial. Okay. And here I assume that the particles are distinguishable in this case. But now if you consider them indistinguishable, you would also add a little n factorial here. Okay? But here I'm considering something much simpler. All the particles can be anywhere. Okay.
Sometimes it's better to specify at the beginning. Because when
I specified at the beginning, I said every particle can be at any side at any time. Yeah. Okay. Is it okay?
it's okay.
Okay. Okay, so you see entropy has a direct connection to arrow of time. The arrow of time at our scale is a statistical effect. Is the fact that systems tend to evolve towards macroscopic states, which have more associated microstates, which translates into higher entropy. So the arrow of time is linked to the increase of entropy. Okay? So from a statistical point of view, it's the same to say the entropy can only increase or we have an arrow of time. Okay? Of course, you can, in physics, you can interpret the arrow of time in many other ways. Particle physics, this would be different. But from a statistical point of view, this is one of the interpretation. Okay? At least at our scales. Okay? At macroscopic scale. Okay, all that is in the notes. It's pretty nice, no? This interpretation, I think, for me, it's quite nice. I don't know about you. Okay. Okay, we'll skip the point 3.3.2 in my notes, which is further details on the link between the second law of thermodynamics and the canonical ensemble. You can read. All right. So when we started the course, the initial goal that we set ourselves was to essentially understand from a different angle why is the Gibbs-Boltzmann distribution the proper law to describe so many things. Okay, why it should have this form. Okay. So one angle we took was just to define an extremely generic class of distributions that are called factor graphs, and to see that it can be simply re-expressed as a Boltzmann distribution. And then the angle that we're taking now is through information theory. Okay, and so we spent a lot of time on understanding what is the main object in information theory, which is information, which is formalized through the Shannon entropy. Okay, and we understood why the Shannon entropy is a proper measure of information or of uncertainty, which is again the same. Right? Now, how can we derive the Gibbs-Boltzmann distribution using in some way what we understood about the Shannon entropy? Okay, this is what we want to do. And so to do so, we'll need a principle, which is called the maximum entropy principle, and that makes a lot of sense, and that allows to derive this Boltzmann distribution from the entropy. But to make this derivation, it is based on the method of Lagrange multipliers. So I asked yesterday if, I don't know if I want to spend, Okay, maybe I can spend 15 minutes on this, and then we start the maximum entropy principle. But who is familiar with the Lagrange multipliers already? 1, 2, you are or not? You're not.
I forgot.
You forgot? Okay. You're not? You say that, and then are you familiar with Lagrange multipliers? And for the others, do you know Lagrange multipliers?
I forgot them.
Sorry?
No,
I
bro.
forgot it.
Okay. So I will be brief, okay? It's not, the method is easy, but what should be done is not so easy. I tried to write a very detailed explanation, which is clean also mathematically, so I will try to describe it now, but I invite you to read the pages 27, 28, 29 of my notes, 2010, which is equal to 30. Okay. All right, but I will describe a bit. So let's see first what type of problem can we solve with this method. It's called constraint optimization. Okay. So the question is that let's say you have some function of Rn to the reals, okay? That is subject to, okay, you have this function, and what you want to solve, so the constraint optimization problem is the following. Optimize f of x subject to g of x is equal to some constant. You can consider more than one constraints. It could be g1 of x equals c1 and g2 of x equals c2, etc., etc. What is important is that the number of constraints n is less than n minus 1, because you see that if you over constrain if you have too many constraints, at some point the space of solutions goes to 0. There are no more solutions. It's like if you have more linear equations which are independent about some variables. If you have more linear equations than variables, you have an over-constrained set of linear equations, and there are no solutions, usually. Okay. Here it's the same. If you have too many constraints, maybe you don't have solutions to this. You have no vector that verify all the solutions altogether. Okay? This is a technical point, but let us consider the simplest case where you have a single constraint fixed. Okay. So what does it mean to optimize this function? Optimizing means find the maxima and or minima, okay, which means the optima of these functions. Okay, so there are some technical conditions on these functions. In particular, we will assume that f and g that define the functions to optimize and the constraint, they are set C1 functions. You know what C1 means? What is a C1 function?
Continuous.
What is a C0 function? A C0 function is just a continuous function,
Yes. First derivative.
and a C1 function is a function that is continuous, and such that its derivative is also continuous. Okay? So this is a C0 function. Okay, this is not, let's see. This is not a function. This is not a C1 function, it's C0 because it's continuous. But you see here you have what we call a cusp or a kink. It's a point where the derivative changes discontinuously. Okay? Good. So in a sense, C1 means the function is quite smooth. Okay? It has no cusps. Anyway. Okay. Okay, do I want to describe all that? Okay, let me try to make that. It will be difficult in 10 minutes. Let me try. So let me define. So the technique of Lagrange multipliers is a technique to find solutions, because they may be more than one. Okay. Solutions to this constraint optimization problem. Okay. More than one because they must be multiple minima and maxima. Okay. For example, this function has 2 maximum and 1 minimum. Okay. Okay. So we'll try not to mix myself. Okay, so let me define S, which is a hyperplane, which means a kind of surface that lives in the original space, where the original space is Rn. It is a subspace of Rn, which will be defined by the points such that g of x is equal to c. Okay? So essentially, these are the points in Rn that verify the constraint. Okay? So we know that whatever the solution to this problem is, it must belong to this surface, to this hyperplane. Okay? It's not called a hyperplane. A hyperplane is a generalization of the line in higher dimension. It's a plane in higher dimension. This is called a surface in general, or a manifold. Okay? It can have a weird shape. Okay? So any solution of this optimization problem must belong to this set of points. Okay? All right. So we know that because the functions were considered they're continuous, this thing is also smooth. Okay? It's a nice surface, I guess. All right. So now let me define E of x let me consider any point x that belong to this surface, okay? And let me define E of x, a unit vector. So what does it mean, unit vector?
One of the axes.
What?
One of the axes is the space.
No, in general, a unit vector is. Sorry?
The length is 1 here.
Yes, so the norm of this thing, okay, which is defined how? What is the Euclidean norm? It's square root of sum of e I squared is 1. Okay? So yes, it has length 1. But this is what it means. Okay? A unit vector, which is a tangent vector tangent to S at point X. Okay, so imagine this surface here that is defined by this set of points that verify the constraint we are interested in. And you take any point on this surface, okay? And on this point, there are a number of vectors. Here I consider one of them, this E of X, which are tangent to the surface. So if the surface at some point is like this, the vector tangent at point X is something like this. Okay? Is it clear? Good. Of course, there might be multiple tangents. Huh? So in 1D, for example, if I look at this point, there is a tangent here and a tangent here. There are two in this case. Okay? So in higher dimensions, there might be a whole family of vectors like this that are tangent to the point. Okay. All right. So what does it mean for a point to live on this surface? It means that if we move a bit away of this point, okay, to the next one, that will also sit on this surface. If the step we do is extremely small, will remain on the surface. Therefore, the value of the function, g, should not change, because by definition, all points of on this surface, they have the same value when you apply this function g. Is it clear? This surface is by definition all points, so that when you evaluate the function g on them, it has the same value. So if you place yourself somewhere on the surface and you move a tiny bit so that you stay on the surface, the value of the function should not change by definition. Okay? How to translate that mathematically? It means that if you take the derivative, but if you want the vectorial generalization of a derivative, so here I take a small number epsilon that goes to 0, and I look at the function evaluated on my point x, again still x belongs to the surface, plus my epsilon times my tangent vector minus g of x over epsilon. Okay, so what does it mean this? I'm sitting on a point here. I look at the variation of my function when I move a bit on my surface by a value epsilon, and in a direction so that I stay on the surface, and this direction is fixed by the tangent. Okay, to stay on the surface, I must go in the direction of the tangent. Okay, is it clear? So this is a generalization of a derivative, and this is what is called the directional derivative, and this is nothing else than the gradient of g, scalar product with the tangent vector, which concretely is what? Is the sum from I to n is the dimension of the space, of the variation of the function with respect to each component evaluated in x times ei, the component of the tangent vector. So it's like if by how much vary my function, it varies by its variation, the sum of its variations along each direction, weighted by the component of the tangent vector. Okay? Because I'm moving this point in the direction of the tangent, which means that if the tangent is like this, for example, there is no variation along this direction. So that's why I need these components here to be there. If one of them, if one of these components is 0, means that I'm not moving in this direction. This quantity should not matter, should not appear. Okay? So this object is called the directional derivative. Okay. This is the basic of differential geometry. Okay. Okay. Is it so? The gradient. Everyone is clear with what is a gradient? Just to make sure. This is the gradient. So the gradient of g of x is the vector of partial derivatives. Okay. This one x, dg, dx2 x. Okay. So it's a vector of size n. All right, so we know that if we take any point on this surface, which is the space of possible solutions, a priori, of our constraint optimization problem, any solution must live in this manifold S. This directional derivative must be 0. Okay? Because we are staying on the surface, and by definition this surface is defined by the set of points for which our function is constant. Okay, so this is a set of equations, okay, for x. Okay. Okay. Now, do I want to say something more here? And here, this dot here is the scalar product between this tangent vector and this gradient. Okay. Okay. So now we know that any points that live on this surface verifies these equations. By the way, how many equations do we have here? This defines how many equations? N. N equations, okay? Because this is, if you want, this 0 means a vector of n zeros. So we have one equation per component. Okay? All right, but this is not sufficient for a point to belong to this surface S, to this surface S, to be solution of our optimization problem. Okay, the optimization problem was defined how it needed to belong to this surface so that it verifies this constraint, but it also needs to be an optimum of the function f. So let's see now how can we write this other condition. Okay, so imagine now that we're not only on the surface, which defines the points that verify the constraint, but in addition we're at an optimum. Okay, we're let's say at a maximum in this case. If I'm at a maximum, it means that if I move around this point in any tangent direction to this surface, the variation must be equal to 0. Okay? An optimum is defined by the fact that the first order variation, which means the derivative, is 0. Okay, when you have in the scalar case, if you have a function f of x, how do you know it? How do you look for an optimum, a minimum or a maximum? You look at the derivative and you equate that to 0. Here a maximum is such that if you move a tiny bit around here by an infinitesimal amount in the tangent direction of this curve, the value of the function does not change at first order. Okay? Is it okay, or you look... You need to speak louder.
I think I just said
No, tell me.
if you move from there to and up, if you're at a maximum,
Yes.
it will still change. But since they are assumptions for different directions.
You mean in the previous slide? Here? Or what do you mean? Like if you are here saying in one dimension, the maximum is such that derivative is 0. Okay? If you change by epsilon, maybe the second order in the Taylor expansion of the function will matter, but that first order, the variation at the maximum is 0. Okay, so you can see that as a definition of maximum if you want. At the maximum, this is true. I cannot redo all analysis right now, but this should be, you should make sure that you understand that. Maximum verifies that. Okay. You knew that, no?
Yeah, but the explanation is,
It's not an explanation.
I just look up.
It's not an explanation.
I'm not justifying anything, I'm just recalling to you that the derivative at the maximum, a function has 0 derivative. Okay? But then, in a higher dimensional space, at the maximum, what is 0? The variation along any direction. So the gradient, okay, if x is a maximum, must be the 0 vector. Okay, it's an optimum in this case, or a minimum or a maximum. It means a minimum or a maximum along each directions. Okay? Okay, so in addition of living on this surface, we need that if we are at a maximum or a minimum, but let's take a maximum, if we continue to move in the direction, to a tangent direction of this surface, we need the variation of the function to be 0. Okay, so for any point x that belongs to this surface and that is an optimum, you need that the directional derivative, which means the projection of the gradient along this tangent direction, we're looking at the variation of this thing, of this function f, but along this surface. Okay, we don't want to move in a direction that goes out of this surface. So we want to stay on it. So that's why you need to project the gradient along the tangent. Must be, so what it is mathematically, it is this, I just write it explicitly. It must be 0. And I realized that I said something wrong here. This was not a vector, I'm sorry. This was just 0 because I take a scalar product. Huh?
Okay.
Okay? I'm sorry about that.
So for that,
So here, yes?
there will be only one equation?
Yeah, at the moment we have only one equation.
Okay.
That was my mistake. Okay, I was thinking already. And here is the same, we have one equation. Okay? But, so what did we obtain? We obtained that if you are at an optimum and at the same time the point lives on the constrained surface, okay, the space of point that verifies the constraint, we have that is equal to 0 and is also equal to this function for the solutions we are looking for x, which is a solution to our optimization problem. Because this condition says that we are at an optimum, and this condition says that we are on the constrained surface. Okay? But what does it mean to have vectors, in this case these gradients, which are orthogonal to the same vectors, these tangents? Because you remember, if A scalar product with B is 0, it means that the two vectors are orthogonal, okay?
But they are not.
Sorry?
But they are not scalar product.
No, this is a scalar product, yes. Here also it's a scalar product. Here I'm looking at the scalar product between the gradient and the tangent vector.
Yeah.
And geometrically, when you do the scalar product between two vectors, you look at the projection of one of the two on the others.
Yeah.
And when the scalar product is 0, it means that they are orthogonal. The projection is 0. Okay? So what does it mean to have these two vectors? So the first one is the gradient of f, and the other one the gradient of g, to be orthogonal to the same set of vectors, which are these tangent vectors E of x. No, they are collinear. So, or they point in the same direction. Maybe they have a different amplitude, a different norm, but they have to point in the same direction or the opposite direction. Okay? If you have vectors that are orthogonal to the same set of vectors, then they must be collinear. Okay? So this implies that gradient of f is equal to lambda gradient of g for some lambda that can be positive or negative, but they must be collinear, which means proportional one to the other. Okay? And essentially this is it. We have proven that the set of solution to our constraint optimization problem is actually, the thing is that you see this parameter here, we don't know what it is. We know that there is one such parameter, but we don't know what it is. We'll have in some way to fix it. And this is called the Lagrange multiplier. So the set of solutions are the points x lambda belonging to the space Rn plus 1, because x belongs to Rn and lambda is just a scalar, such that gradient of f in x is equal to lambda gradient of g in x, and we also should not forget our constraint, which was g of x is equal to c. Okay? So this is how many equations? This is really n equations. We have one equation per component. We have an equality between two vectors that live in Rn. So we have n equations. And here we have an additional equation. And so, because the space here is of dimension n plus 1, we have n plus 1 equations. This fixes the solutions. Okay? So this is the recipe. The recipe is if you have a constraint optimization problem, the solution that you're looking for verifies this n plus 1 constraint. So what you do is that you compute the gradient of f, you equate that to the gradient of j. This defines n equations. Then the last equation you're missing in order to fix the value of the Lagrange multiplier is the actual constraint. Therefore, you have a set of n plus 1 equations that you need to solve. And this gives you the solution. Okay? Okay. Let me just show you an equivalent formulation of that to the introduction of what we call the Lagrange function. And this is how usually people actually solve this kind of problem. It's totally equivalent to what I will say, as you will see directly. It's just that it's a nice interpretation. If you define L of x lambda as the original function you want to optimize minus sum from j equal, by the way, yes, when you have more than one constraint, yes, before writing that, let me, oops. When you have more than one constraint, you can generalize the argument that we did, and what you obtain is that the set of solutions is given in this case by the points x lambda, where both are vectors, belong to Rn plus m. Let's say you have m constraints, such that the gradient of f in this case is equal to the sum from j equal 1 to m of lambda j times gradient of the j constraint, and jgx is equal to, say, cj for okay, so this is the same, but now we have m constraint. Okay, more than one. In this case, what you need to align is not just the gradient of f with the gradient of g, but it's the gradient of f with a kind of weighted combination of the gradients of all constraints, which is this sum. And the Lagrange multipliers are the weights. Okay.
Is that lambda in the bracket next to x?
Yes, this is the vector lambda that belongs to Rm, and this is the vector x that belongs to Rn. Here it's in the case of m constraints. Okay? So find the optimum of f of x such that j1x is equal to c1 and j2x is equal to c2, etc., etc. You have m of them. Okay? The space of solution is given by that. So you have, again, n equations here, and you have n equations here. So the problem is well defined. You can find a solution. Okay? You have n plus n equations to find a point or a set of points in an n plus n dimensional space. So it is fixed. Okay? So the Lagrange function is what? It is defined as L of x lambda, which is the original function, minus, I consider the generic case with m constraints, okay. So why did I introduce this function? Because the unconstrained optimization problem for this function is equivalent to the original constraint optimization problem. Why? If you look at gradient of L is equal to the zero vector, which is the unconstrained, unconstrained optimization of L is find x such that gradient of L, and actually it's a point x lambda, equal to the zero vector. And indeed, if you compute this gradient, what do you get? You get the you get df over dx. One, this thing does not depend on sorry, what am I saying now? Wait. No, it's correct. If you compute this gradient, you get the derivative of this thing with respect to x1 is df over dx1 minus lambda 1 dj1 over dx1. Okay, tac, until df x n minus lambda n dj. No, I'm doing something wrong. Doing something totally wrong. Yeah, but this is great. No, sorry. Excuse me. I don't know how to compute the gradient anymore. This is what? This is df over dx1 minus sum over j to m of lambda j dgj over dx1 df over dxn sum of jhn xn, and then you have d, the gradient, the derivative, the partial derivative with respect to lambda 1. This does not depend on lambda 1, this f. So you simply get, and this does not depend on lambda 1, you just have a linear dependency like this in lambda 1, so the derivative is trivial. You get, if you want, you get j1 x minus c1 jn x minus cn. Okay, this is the gradient. Is it clear? Because it was not for me, so is it clear? And you see that if you equate that to 0, this is exactly the definition of this set. The first equation here is the first component of this equation. You agree? This, the first component of this thing being equal to 0 is the same as this being equal to 0. You agree? The second component of this vectorial equation being equal to 0 is, sorry, the last one is this one. Not the last one, the n1. Okay? And now this equation is this equation being equal to 0. Yes or?
Yes.
Do you understand?
Yeah.
Do you understand? You have to say, you have the right to say no. Okay, it's great. So you see that we converted a constrained optimization problem of a function, that is to find the optimum of some function under the constraint that the solutions must verify this type of constraint here, into the unconstrained optimization problem of another function, which is called the Lagrange function. And indeed, if you equate the gradient of these functions to the all zero vector, it gives you a set of n plus n equations, and finding the solution of that is the same as finding the solution of the optimization, the constraint optimization problem. Okay? So, what did I ask you to do for tomorrow? Proving the properties of the Shannon entropy. This should take you 20 minutes. Writing the posterior for the BSC channel. This should take you 3 minutes with what we said today, or 5 minutes, 10 minutes, okay? Otherwise you will, no, I didn't. Take your time. It should not be complicated. It's a very simple generalization of what we said today. And other exercise that I invite you to do is the exercise 5 in my notes. Is to actually solve a simple constraint optimization problem using the method of Lagrange multipliers. Okay? So tomorrow, last course, it would have been nice to have an additional course because I'm a bit late with this. Maybe I can do it. Yeah. Tomorrow we'll finally reach our original goal, which was to derive from in a very principled way the Boltzmann distribution. And the way we'll do that is by using the so-called maximum entropy principle. And you will see what it means tomorrow, and it's an extremely powerful principle. extremely general that applies to essentially all fields of sciences, and that has a very deep meaning. Okay. Okay. Any question from you or the others? Just if it was not totally clear, you see that this thing is the same as this because I can also rewrite these things by putting a minus here and equating these things to the old zero vector. And here I can put a minus and equate this to 0, which is exactly this. Okay? A equal B is the same as A minus B equal to 0.
Can I ask?
Yes.
C is a constant.
C, yeah, the C's are constant. Yes.
So the G
Is a function and a constraint function.
Yes, you were saying.
G is not a vector.
What is not a vector? This? No, this. I'm sorry if I didn't say it. If I didn't define it here at the beginning. The G functions here are also from Rn to R. They take as input a vector and output a scalar. Okay? And what it means to be C1 for a function of a vector to a scalar means that the gradient is continuous. The derivative is continuous along each direction. Okay, so it's a smooth function. Like the output of this function is continuous, whatever direction in which you move in the input space. Okay, it's continuous with respect to all input dimensions. Okay. All that is not easy, but I hope it's clear enough so that with the notes it should be okay. And you can always come and ask questions. You know where my office is? Yes.
Which number?
216, I think.
216.
You know where Jacopo is? Or it's all the.
Yes.
We are all in the same corridor, and all the QLS group is at the same place. So. Okay, see you the others tomorrow.
Thank you. Bye.